Great, well, thanks for making it out tonight. So my name's Isambard Poulson. I'm one of the founders at Huck Industries, and I look after the tech team there. Just a little bit of background about me. I've had quite a varied career. I studied science, I've been a management consultant, I've worked as an artist, a lecturer, but for about the last 15 years I've been working as a technologist, mostly in mobile, and then more recently in data analytics. So I love to share the things that we've learned. So we've had a journey about 4 or 5 years long, and we've definitely made a bunch of mistakes in that, learned a lot of lessons. Hopefully some of you can take some of those away this evening. So Huck Industries. Huck Industries was founded in 2014. We're a geolocation company. We use mobile data to provide insights and provide data and analytics into a variety of verticals. So those include financial services, both quantitative and fundamental funds, property, consultancy, and planning, also out of home, which basically like billboard, advertising, essentially any application where you want to be able to understand the macro behavior of people at large scale and how they move in the real world. So, so what I'm going to talk about kind of is a brief overview of some of the things that we've learned, but by no means covers all the details. If you'd like to know more, and please feel free to grab me afterwards. So that's about it. So for now, I just want to rewind a few years back to about 2015. We'd recently raised our first seed round, and we're basically setting out to build our first product. So at this point, our focus was very much around providing insights to application developers that provided them ways of understanding the context in which their users were using those applications. So essentially, it would enable those guys to build experiences that changed depending on where the users were. So if a user was on their way to work, the experience they got might be different to that if they were, say, in retail environment. At this point, all we had to do was get some clients and build the product. So the product was a web-based dashboard. In case anyone's ever built web-based dashboard, I don't recommend it, but feel free to give it a crack. And we're deciding that we built that ourselves in order to surface the analytics that we were creating. So we had this highly defined vision of what it was going to be and a very short time scale in which to do it. We had a newfound group of investors, and they were keen to see results. So we basically went full steam ahead on development, and about 2 months later had a product that was almost live, not quite. And so it was a fairly rigorous, hard-nosed process of axing features and basically forcing it to go live. And that enabled us finally to launch in the early part of 2016. It was really only at that point that we could reflect on what we'd made so far and basically understand it. And that's why I would strongly recommend anyone who does this sort of thing to just seriously push towards going live as fast as possible. They say that if you aren't embarrassed by your first product release, then you waited too long. So I can certainly say that we didn't wait too long. I'm just going to now show you our first. So brief caveat on this first architecture. So basically, I'm going to tell the story of our development principally through 3 primary architectures that we've developed. So it's almost one a year, not quite one a year, but essentially it kind of it provides a way of kind of tracking our progress through our journey. This point, it's pretty hard to think really modularly when you've got a very, very tight time scale, and also that you have, in a way, thought about your product as only one thing. It was only ever designed to do one thing. It had one singular purpose. That was the vision that we had. And so we didn't really start building it in a way that was adaptable. But so data would come into Nginx, and that would be passed into our primary processing application. which would do a bunch of third-party lookups, and then dump that data into the database. So all of this is happening synchronously, because at this point we want to return a response to the client. We then have a secondary analytics application, you could call it. Essentially, this is building insights, building roll-ups from the data, and exposing those to the client via dashboards. So this was great. It worked. And yeah, it was live, it worked, clients were liking it. But what we realized at this point was there was in fact a much larger business opportunity here. And that probably we weren't going to, just providing these insights to application developers, might not be the only long-term thing we could do. In fact, it's quite hard for those guys to take action upon those. And yeah, it was, anyway. Other things to think about, but that we could aggregate this data, anonymize and aggregate this data, and then make that available to other people who would be interested in these aggregated analytics. So at this point, we embarked upon a data recruitment drive, because essentially we were going to need a lot more publisher data in order to perform this. Naturally, looking after the engineering, the question I was asking was, well, what happens if we end up with a lot more data than we can process? The answer was, well, that would be a nice problem to have. I don't know if anyone's ever heard anyone say this, but if you do, you should meet it with a mixture of emotions. One of those should be fear. Basically, a couple of weeks later, don't worry, I'm not going to do any live coding, but a couple of days later, this is like what the server is looking like. That's the extent of the live coding. So we did what any right-thinking technical team does in this situation, and that is scale vertically, of course. So basically, buy a bigger server, and next week, buy a bigger server, redeploy the same code again on a bigger server. At this point, we were growing our data volume at a rate of about 100% week on week. So pretty much within about 6 weeks, we were on the largest box that you could get at OVH. And it was obvious that there were some more fundamental things that we need. I wasn't expecting to get so many laughs, actually. But yeah, I mean, it's a tried and tested approach. So what we realized, of course, is that we really needed to revisit the way the architecture itself was organized. So if we go back to our diagram, the main problem we had is we have a lot of elements here which are extremely closely coupled. We have synchronous tasks, passing data both into the primary application, looking up external data sources, tying to the database. We had like Nginx timing out over 20 seconds to reply, deadlocks on the database. Basically, it was ugly. Fortunately, one of the things that had come out of our shift in focus, which was to not reply to the data immediately, was that some of our requirements had shifted. And so one of those requirements is we didn't need to return any data in the response that came into us in Nginx. So we could basically just create a small application which just would then dump that data onto a queue. So we chose Kafka, but there's obviously lots of other options. So now in this scenario, like that top left application is tiny little application. It literally, all it did was consume the data, dump it on a queue, and return 200 immediately. So immediately this had a very positive effect. We could then consume the data from that queue at whatever the speed that we liked. And immediately the whole system was significantly happier. Basically, an additional benefit is like the queue then was smoothing out bumps in the data. So we would have traffic that varies across the day. Naturally, we would have like spikes at certain points. And this would then enable us to like smooth out those spikes. So it was at least stable. We're getting 200 responses on all of our requests. Stuff was not timing out. Database was happier. And so I think it's interesting to reflect at certain points on things that happen that have a long-term impact upon your architectural decisions. And one of the things that we learned here was that of all of the things that had broken, so we had inconsistent databases with periods of data that were maybe, like you could say, faithful, and bits which were unfaithful, various logs of various places which were broken. One thing that was consistent throughout all of this was the Nginx logs. So those then became kind of our single source of truth. You could think of it like that. We had unbroken history of those. So we had then at least now stable system, if not capable of reprocessing all of our data history, at least reprocessing some, and it was working. So this is a bit of an interlude. I didn't really know quite where to drop this in because it's not specific to any particular piece of architecture or any particular development that we made. We used it across time, basically from about this time in our development. It's something that we've just found to be like super duper useful, basically, in a variety of applications. So initially we used it as a technique to support us when we were migrating individual pieces of architecture. So what it would enable you to do would be to say here, data coming again to Nginx, being forwarded onto a particular port, then have our primary application listening on that port. What you can do is use a tool such as Go Replay. Go Replay's been one of our favorites over time to mirror the traffic that's coming into that port. So you can then spin up alternative application and test, basically, that everything's working fine before before deploying your dev application into the live environment. The cool thing about it is you can just keep doing this as many times as you like. So you can have potentially multiple applications all running off the same primary data. We've in fact used this for a lot of different purposes. Load testing is particularly powerful. So instead of forwarding all of the traffic to different applications, you can then duplicate it as many times as you like and forward it all back to the same application. So we found simulating live data kind of tricky using more conventional load testing tools. Often the data that's generated by them is kind of formulaic, and we prefer to test basically using data as it would be from as our live stuff is. And we still in fact use this technique to create fully redundant backups of our live data. So essentially duplicating it. Nginx now also has this function built directly into it, so it's called the mirror directive. It's really awesome. So we now actually use Go Replay less, and this is what we often use for creating our redundant backups. And what is cool about both of these ways of doing it, I'm sure there's loads of others which we haven't discovered, is that they're really, really resilient. So we've had servers that have fallen out of sync with AWS, for example, and can't upload their data to S3, fill up completely with logs, so you virtually can't connect to them, and these services will continue running. So on more than one occasion, these have saved us in terms of helping us to maintain full historical data integrity. So I strongly recommend trying them out if you have any need to process real-time web traffic or requests. So anyway, back to kind of like the new requirements that we had on our system. Basically, as we'd shifted, there were some ways that we could probably capitalize on kind of our new client base or our new orientation. And there were also additional challenges. So, so the first of those is that we didn't any longer need to be able to process the data in real time. And this was a really big thing for us, basically, because it meant that we could then batch the data, we could store it. We didn't have to design a system any longer where all of the elements are like super tightly connected. We could have a much more decoupled structure. So it took us a while to really think, and kind of talking to clients to discover that they didn't actually want this, because I think it's easy to assume that, okay, people want stuff like immediately, and in fact, almost all of the people that we sell our insights to don't actually want it immediately. 48 hours after real time is completely fine. So yeah, this enables us to process the data in batches, enables us then to run cleanup processes after that, and deliver it to client-facing locations and check its integrity all before those guys want to be able to pick it up. Secondly, though, we wanted to be able to meet scale requirements for the future. We're now firmly in a growth phase, and it was no longer enough to merely be able to be comfortably processing data at our current level, but we needed to really be able to anticipate growth as time went on and be confident that the system is not going to, kind of fall to bits. And thirdly, we needed to be able to reprocess our historical data. So often we want to be able to make ongoing changes to the code base, and for many of our clients, they're building models, they're training models against the data itself, and they want the full history to be delivered in one consistent state. It's not enough to, it's not acceptable really to just be pushing changes to the code base so that the ongoing stream is changing as time goes on. We want to be able to deliver full history, all processed in one single way. And so, basically, we had these are kind of the things we need to be able to do. So we were obviously, well, not obviously, but maybe wanted to move to a kind of more serverless infrastructure. So we're a tiny little team. Basically, there's only 6 people in the company, and deploying your own infrastructure can be really onerous. It's not only the deployment, you've got to monitor it, check everything's okay, and all of those sorts of things. So, we were after solutions that would scale smoothly, where we didn't have to do so much of that, and so we started using AWS Lambda. Basically, for those of you who haven't used it or don't know what it is, AWS Lambda is a compute service provided by AWS. Essentially, you can run any code base on it. It will be invoked, and it will be essentially, you can run any code base that you don't need to persist for more than 15 minutes at a time. So it's invoked, it stays up for 15 minutes, and during those 15 minutes, you can do whatever you want. So you can communicate with databases, external data sources, but it will be destroyed 15 minutes later. So that's basically what it is. So this is how now our architecture would looked in its new iteration. So data comes onto the platform. We're now running Nginx inside Docker and put this on a number of different nodes. So this sits behind an AWS service called Route 53, which is a latency-based DNS service, and then put these containers onto a bunch of load balanced nodes, so we can just spin up more of those whenever we want to be able to handle more traffic. And that then periodically just dumps the data into AWS S3. Now, what's cool about Lambda is that you can set it to be triggered when a new file arrives in S3. So we set ours to be, so that Lambda will pick up the new file and then just basically process it. We're then connecting our persistent data on RDS, AWS RDS, which we're running Postgres RDS, and then when it's complete, it's pushing the output data to client-facing buckets, and now also to Google BigQuery. So this is actually kind of a compressed diagram of how it actually works. There's actually a couple more stages in this, but essentially this gives you conceptually the way it works. Further benefit, so this was now super powerful. And what's cool about, this is like just the more data you put into S3, the more lambdas get invoked. You don't have to worry at any point about provisioning more infrastructure. It just essentially scales smoothly. Another cool thing about this way of organizing it is that we could then have like green-blue deployments. So we would basically completely mirror the architecture and then have those running inside two different VPCs. And but essentially this means that you have essentially dev and live environments which are running identical architectures. Everything about them is identical. You can deploy to whichever one isn't your current live and check everything's fine before switching over to it. Results in, for us, it was really good because it means we can do fewer deployments and resulted in a kind of better level of checking the integrity of new new commits, basically. 5 minutes. Okay, I'm going to speed up because I've only got 5 minutes left. So, some of the benefits. So fully auto-scaling, more data you put in, the more lambdas you get. Super simple, and then also, your cost scales directly as a result of how much compute you use. That's pretty cool. But there were lots of problems, basically. Not lots of problems, but some problems. One of them, particularly for us, was the stability. So in this scenario, what we would find would be that essentially exists in a kind of locally stable state. If it would be running fine under normal circumstances, but it's quite easy to throw it out of whack. So if a Lambda failed, for example, it would be retried. We would set them to retry, so we didn't end up with holes in the data. And that problem then of retrying can often exacerbate the original problem. So if that's a database-related issue, like connection count or database load, essentially the problem spirals out of control. So it wouldn't generally write itself. Also, there's an upper size on how much of this you can use. I think only 1,000 simultaneous invocations of Lambda. So that was kind of stuff that pushed us on to further things. Ideally, we would like to be able to have not just 2 pipelines, as many pipelines as we liked. Resilience, I've just mentioned, and also the pace of reprocessing. If you think of essentially at that rate of about 1,000, that would take us historically maybe between 1 and 2 months to reprocess of our full data history. That's a long time. So we chose to move to Beam. And so Beam is super awesome, basically. It kind of brings distributed computing to the masses, I think. It's essentially a library that enables you, it's language agnostic, enables you to write your code in Python, Java, I think there's other options, and then you can run it on whatever MapReduce runtime you want. So that supports Spark and Flink. We chose Google Dataflow, which, so this is a brief distributed programming guide. In distributed processing, you kind of have to think about your data pretty differently, and this in this model, then you kind of think about your data as a stream, and each step in the processing as a transformation applied to that stream. So you can no longer really think about having a single overarching application state. You have to think about essentially, or think about kind of sending data to a method and getting a response back. You just think about transforming the data through a set of processes. So we chose Google Dataflow. As mentioned before, small team, love fully managed services. insane amount of potential power. Basically, you can run 1,000 compute engine instances on any job, and even a general compute engine instance can be up to 96 vCPUs. So there's a ton of power. You can run 125 jobs concurrently. That's even without asking them to raise the thresholds, which I'm sure they would do. So yeah, this was a no-brainer for us. And there were a bunch of hurdles that so we entered this project with like a lot of enthusiasm and super high hopes that it was basically going to be this like magic bullet for us. But of course, at various points, we just hit these kind of what felt like brick walls. But we navigated them each successfully. I'm not going to go into depth of these because it's about to run out of time. But if you'd like to talk, I did another talk recently where I discuss each of these in kind of a bit more depth. And so finally, this is how our infrastructure works currently. So code is pushed to GitHub and then run on Circle CI. If the tests pass, we merge the branch into release, and at that point, a Google Cloud Composer template is pushed up with the new version incremented. And that Cloud Composer then runs the pipeline on a schedule. So we're running this on a daily schedule. And then the data is outputted into Google BigQuery. Cool thing is that you can run as many of these as you want. So you just increment the version, spin up a new template, have a new completely parallel architecture, turn them on and off as you want. Super duper awesome. So thank you very much. That's about it from me. Just a quick note, we're not hiring, but which I know is a shock. But I'm always interested to meet people who are interested, anyone, smart people, scientists, engineers, etc. So,
thank you very much, Isambard. We have time for a couple of questions. Do we have questions around the architecture? Where will we go? Go ahead.
Oh,
sorry.
Yeah. Cool.
Go on, Charles.
I've found with Lambdas that the runtime has some interesting deficiencies. So there's no proper multiprocessing, so you can't use pools, you've got to use pipes. It's compiled without SQLite, so you've got to monkey patch it to get Scrapey to work. There's the question coming, sorry. It's a little bit interesting that FFmpeg's MP4 codec started breaking just as soon as they released elastic transcode. What was your, other than the scale, the ceiling on scaling, what was your sort of most interesting deficiency of the runtime?
Yeah, we don't do anything super duper exotic, to be honest. So, yeah, we did try and really work out what is it under the hood. Like, I think it's basically some kind of container. Yeah, we didn't encounter any problems with package management or any particular things. But as I say, it's like a lot of our stuff is, I would say, fairly vanilla. We're often not, we do use external libraries, and what we would do is we would like roll everything up into the code that we would push up to AWS. So we weren't installing stuff after the Lambda was initialized. We basically like bundle up all our requirements and push them up beforehand. So yeah, I don't know if that answers your question, but it didn't have any super nasty.
There's, for anyone's interested, it's Googleable. There is a Docker container that pretends quite nicely to be the Lambda environment.
Yeah, right. I think that's what we worked out in the end.
Predictable ways.
There's a button.
I noticed some of the pain points you mentioned on the first architecture were around like consistency and stability. You'd built everything around a lot of synchronous functions that had a tendency to fail and blow holes in your data. By the time you'd built, I think, the second or most of the way to the third architecture, you centered everything around S3, which is eventually consistent, and you're processing all your data with Lambda, which is, maybe if you're very lucky, eventually executes once, twice, or many times. Was that a consequence of shifting requirements, or did you repeat the mistake a little bit?
So it's the question about consistency. Yes, basically, records as they come, most of those processes are kind of like idempotent. Doesn't matter which order they happen in, basically. So the code is written so that if you were to process records from yesterday today and then process today's records tomorrow, whichever way around it is, it wouldn't make any difference, basically. Yeah. So yes, as time goes on, the way in which the data that we ingest interacts with the persisted stores ultimately all shakes out. So we don't essentially need highly consistent. In Beamland, you can't basically use transactional databases anyway in this way. So we essentially load all of the data into P collection, all of the data that would be in a transactional database into P collection at the beginning of the batch, process that throughout the stream, and then write it all back at the end. But yeah, the problems we were having in the first iteration were really mostly about load and just essentially asking Postgres to do too much work all in one place rather than necessarily anything specifically associated with consistency.
We should take a break now, so if you could save your question for the break. Isambard, will you be in the pub afterwards?
I will be in the pub afterwards.
So there's an option to ask Isambard questions now during the break and then in the pub afterwards. Let's give Isambard a round of applause.